different atoms in different directions. Then you can choose to work with the symmetry operation of the small group of Q, so at least this will not mix different Q. And so what the phonon does, it will construct the small group of Q, so all the symmetry operation that leaves Q invariant or transform it in Q plus a reciprocal lattice vector are used, but the other not. And then the displacement pattern are constructed in such a way that they transform into each other, but with the lowest possible number of patterns that transform into each other. And one can show that if one takes displacement that are basis for irreducible representation of the small group of Q, for a usual Q point, one has a maximum of three displacement patterns that transform into each other. If instead one is into a zone border with a non-symmetric group, it might happen that this the size of these representations are larger, up to 6, and in that case one has to do simultaneously 6 perturbation. So the program Th.x solves this self-consistent linear system by 3 multiplied by number of atom perturbation at a fixed Q vector. And when it has for all these 3 multiplied by the number of atom perturbation the response of the charge density to this phonon of a given Q, it can calculate the dynamical matrix, the complete dynamical matrix at the given Q. And it can diagonalize it and obtain the phonon frequencies at that Q. In principle, this solves our problem we have for the given Q, the frequency, the 3 multiplied by the number of atoms in one unit cell, phonon frequency, and we can plot the dispersions even calculating all the Q of a given plot and diagonalizing the dynamical matrix in all these Q. It's clear that this is a very time-consuming procedure, and there is a way to make the calculation faster. And this is done with the following trick that use the properties of the dynamical matrix and the Fourier interpolation, basically. So let's return to the expression of the dynamical matrix of the solid, as we have written at the beginning. This function, if you look at this function as a function of Q, is periodic into the reciprocal lattice vector G. So the dynamical matrix Q plus G will have here a Q plus G, and here there are Bravais lattice, so the product of Bravais lattice multiplied by reciprocal lattice is 2 pi, and this expression does not change. So since this is a periodic function, what we are writing here is the Fourier expansion of a periodic function. So since this is periodic, it will have a Fourier component only at discrete values of this difference R mu minus R mu. And these discrete values are indices by the Bravais lattice vector. The expression of the Fourier transform is this one. So it is the inverse Fourier transform with the minus of this of the Fourier transform. In principle, here we should do a continuous integral. So this is an integral over all the Q vector of the Brillouin and so on. So this is an integral over the Brillouin and so on. In practice, in the computer, what you can do is if you have a have a function, a continuous function, you have to discretize it. And if one discretizes it, one has to use the property of the discrete Fourier transform. Which are the property of the discrete Fourier transform that are relevant for this problem. So let's remind a little bit this point. Let's consider just a one-dimensional periodic function f of x such that f of x plus a is equal to f of x with period a. This function can be expanded in a Fourier series, and the Fourier component are just 2 pi divided by a and multiplied by an integer number n, where n can be positive, negative, or 0. These coefficient Cn are a continuous integral, so they are 1 divided by the period, the integral from on a period of the function f of x multiplied by the phase factor. Now, if we substitute this continuous integral with a discrete integral, and we sample the function f of x into endpoints, we obtain an expression, this expression, so delta x, let's take for the endpoint a uniform mesh, xj equal j multiplied by delta x, where this delta x is a divided by n, and this j goes from 0 to n minus 1. So this delta x is a divided by n, the a and this a simplify, so we have a sum over j that goes from 0 to n minus 1 of this f of xj multiplied by this phase factor. So instead of kn we put 2 pi over a multiplied by n, instead of x we put j multiplied by delta x, so j multiplied by k and n, and here we will have a phase that is 2 pi divided by n and j. So this object is our approximation of the real Fourier component that we can indicate with the C tilde of n. And this approximation of Cn could be a good or bad approximation of this Cn depending on the property of the function f of x. In particular, if f of x is a sufficiently smooth function, then you can show that the Cn goes to 0 when n becomes very large. And instead, this approximation that we have of Cn does not go to 0 when n becomes very large, but this is a periodic function. So if here instead of n you write Cn plus the number of points, well, if you insert this expression here for this n, you will obtain the same object. So this will be a function such that Cn plus n is equal to C tilde n plus n is equal to Cn. So it might happen that this n, so this n is the number of points in which we sample the function. If this number of points is sufficiently large that the true Cn is already 0 after n divided by 2, when n modulus of n is larger than n divided by 2, then this periodic function, this approximation of Cn, is a good approximation of our original Cn that will go to 0 in all the points that outside the interval minus n half divided by 2. Minus n half divided by 2 and half divided by 2. Instead, if the n is small and the real Cn has not become 0 outside this range, then this cannot be a good approximation of our Cn, and we will have what is called an aliasing error. So, if we approximate our function f of x with this taking as Fourier transform the C tilde n, we will obtain a continuous function that will be similar to the continuous function that if this Cn tilde is a good approximation of Cn. Otherwise, it will coincide with our original function at the point in which we constructed C tilde n, but will not be a good approximation in the other points. So in our case, how does this is this relevant for our case? So in our case, we have our continuous function that is the dynamical matrix, and we sample it in a certain number of points, qi. So doing this sample, we will obtain an approximation of the real interatomic force constant. If we are taking a mesh of q points sufficiently large, then that the interatomic force constant that cannot be described by this approach because our approximation is lattice periodic. If this interatomic force constant in the real system were already zero, so if these are short range and go to zero, where our approximation becomes periodic, well then the approximate interatomic force constant that we calculate are a good approximation of the real interatomic force constant. And
how about long range? How about long range interaction, like dipole interaction is included?
Yes, exactly. So if there is a long range, if there are long range interactions, we have first to subtract this non-analytic part from this dynamical matrix, that in such a way that the object that remains has a Fourier transform that decay rapidly in real space. And then what we do, basically with the procedure that I will show you, we obtain the analytic part of the dynamical matrix. The non-analytic part, so we interpolate just the analytic part of the dynamical matrix. The non-analytic part must be, it is due to dipole-dipole and can be calculated numerically. It can be added after this Fourier interpolation.
So how could you determine the size?
How do we determine the size of the interatomic force constant? One way is that we do the calculation with different mesh of q point and see when the interatomic force constant converge. So we enlarge the size of the mesh, and at a certain point our interpolated phonon do not change anymore. The other method is that when we have interpolated the phonon, we can try a few phonon calculation with all the machinery of density function of perturbation theory at q vector that were not in the original mesh. And we can see if in that q vector our interpolation is good or not. Okay, so to simplify the notation, we can write like this, just to make the link with the review of modern physics. We can write the discretization introducing this C matrix, that is the dynamical matrix multiplied by the square root of the masses, and then our approximation of the interatomic force constant is given here, a sum over q point. So we calculate with the phonon code the dynamical matrix in a mesh of q point, this qi, and then we use this Fourier transformation, Fourier discretization, to calculate the interatomic force constant for a certain number of neighbors. the number of neighbors will depend on how large is the matrix of the interatomic force constant. Okay, since this second derivative depends, does not depend on mu, but depends on the distance between mu and nu, we can put an r here and define r as this difference, and call also this interatomic force constant as c of s alpha s prime beta of r, just of the distance from the origin. And that this r is the distance of r mu and r nu. And so these interatomic force constant are calculated starting from the dynamical matrices multiplied by the mass that are calculated on a uniform mesh by doing a Fourier transform. This Fourier transform, well, this is a discretization of the Fourier transform. This operation is done by the code Q2R.x. So once we have the dynamical matrix into a mesh of Q point, we do this Fourier transform and obtain the interatomic force constant for a given range of neighbor of the origin. Once we have this, then we can apply the direct, so the link between the definition of the dynamical matrix that gives that the dynamical matrix are the interatomic force constant and then the phase factor, so the same definition that we have seen before, and we can use here a Q point, arbitrary Q point. If these interatomic force constant are a good approximation of the real interatomic force constant, then this interpolated dynamical matrix is a good approximation of the real dynamical matrix that we would have calculated by using directly phonon.x. And with this procedure, having the interatomic force constant, we can get the phonon at arbitrary fine mesh of Q point, or at arbitrary Q point along a few lines to do phonon dispersion. This procedure, so this Fourier transform, is done by the code matdin.x. So one has first to calculate the dynamical matrix in a mesh of Q point to obtain phonon dispersion. Then to use Q2R to obtain the interatomic force constant, and then use matdin.x, giving as input all the Q vector that in which you want to do the plots, or a very fine mesh of Q point if you want to do, for instance, the phonon density of state. Okay, I think this concludes the lecture. So this afternoon we see the example with Nicola of the use of these three codes, Pw.h, Q2R, and